Today we're going to talk about making smart open source decisions and how that all roads, I say, lead to Kafka, and we'll get there eventually. But we'll start with some high level stuff, some theory, some best practices, and how to take things forward. So kind of the most important thing to do when you consider using any technology in general is, but this is extremely important with open source, is you have to evaluate the overall health of the project. So, you know, when you're thinking of, okay, you Googled, you found some code, and it looks like it'll solve your problem, that's great. But the last thing you want to see is what's like, what we call a dead project. You know, the number of commits have basically dropped to 0. The number of contributors has decreased. Something on the left is kind of a mixed bag, but overall there is one positive indicator. The number of contributors is increasing. So that means a lot of people are adding to the project, but the number of actual commits basically could mean the project is maturing. You know, if this is a brand new project, you'll see the number of commits decreasing. There could be a lot of outstanding pull requests. So, you know, Kafka started in 2009. I think or production release was 2009, so it's a fairly mature technology. So here's a very important diagram over here on the right. This is just Google Trends. So whenever you're looking at a technology, just search that technology, and then, you know, search competitors like OpenStack versus, put that into Google, and then you'll see a bunch of other technologies. So CloudStack is one of them that was used, and as you can see, it's kind of, well, it's completely dead. Yeah, it's completely dead. So OpenStack is still fairly popular. But that's kind of like big picture what you need to do when you're an engineer, when you're a software developer. So I don't think anyone here needs to be told not to learn Fortran. Don't use Fortran. You could use C for college, but after college, I mean, unless you're doing like high frequency trading and you're a quantitative developer on Wall Street, that's like the only industry I think it's used right now. They're very well paid, but it's a very small industry. So let me talk about a promising open source project. This is a project that lived fast and died young. I think we all know that philosophy, right? So Koros had its first stable release in 2014. So this project is very new. You know, as I said, Kafka started stable release 2009. It's very well widespread. And, you know, Koros was a operating system, a Linux distribution designed specifically to run inside a container. And it reached end of life this year. So here's a project, very promising. It was invested by Google, and then they decided, nope, not a good idea. Why do you think this project wasn't successful? And this applies to most other open source technologies, by the way. So kind of the big picture here is sometimes the cutting edge does not mean it's the most viable open source project. So when you're looking at any kind of technology, you know, CoreOS was extremely sexy in 2012. It was extremely cool in 2013, maybe 2014. It was all over Hacker News and boom, gone. Another project I was personally a huge fan of was, well, yeah, I mean, one project I was personally involved in. Have you guys heard of the One Laptop per Child? You know, the $100 laptop? So that was my first software engineering project. And there I learned how to code, you know, in Python. I learned how to program on these tiny machines, and it was a lot of fun. There was like an emulator for it. It was a good project. And it never took off either because people realized that they didn't have to do that. So this chart basically explains the entire problem with CoreOS. It was a crowded market. I mean, if you look at the server market share, first of all, 50% of all servers are Microsoft. So that right there, I mean, unless you're building something for the Microsoft world, you're kind of like, you know, limited to half of the market. Okay. And then there's Red Hat Linux, which is the enterprise market. But that's for like, you know, enterprise, you know, on-prem data centers. So if we just look at Linux distributions, which CoreOS is part of, where does CoreOS go on this chart? Yeah, it's under Other. So it's not even on this chart. It's basically a majority of Linux distributions out there is Ubuntu first. And then, you know, Fedora and Red Hat, because Red Hat, you know, is an enterprise distribution of Linux. And when I started Linux years ago, SUSE was also a player. They're not really such a big player. So yeah, I mean, that's kind of why CoreOS didn't take off. Like all these major incumbents basically saw what CoreOS was trying to do, which was kind of innovative, but really it wasn't earth-shatteringly different. And building a Linux distribution is not easy, so they didn't solve the right problem. They basically had an approach, and other distributions like Ubuntu made smaller images, and Docker got better with Linux. You know, by default, Linux is tiny. So sometimes the most cutting edge is not the viable solution, and I'm even going to say the most horrible thing on the planet. If you know SQL, you can stick with SQL. I mean, look, it's pretty simple. Everyone likes to say NoSQL. Everyone likes to say go away from SQL. But, you know, having seen the code made by developers, some SQL code you just need. Now, there are limitations to MySQL, and we'll come on to that in the next couple of slides. But, you know, if you want to build a transaction processing system and you need to roll back an entire chain of events, which would be in a stored procedure, that's when you don't want to use a NoSQL solution. That's when you should actually use SQL or plan on writing a lot of code, which you can do. But the point is, you know, the SQL is mature technology. It's basically built for transaction processing and permanent data store. Is it designed for the highest amounts of data volume? No, it's a single threaded solution. It's only designed for one client at a time, so you can't do parallel, you know, jobs. It just doesn't, it's not in the DNA. It just doesn't work. So yeah, stick to SQL sometimes. So let's talk about the historical perspective on various other database technologies. So basically in the 1980s, we had standalone machines and mainframe computers. Then in the 1990s and 2005, we had networked computing. Then finally, we had real-time web and big data systems. Then the early 2000s, we wanted to basically throw money at the problem, build a giant Sun Microsystems vertical computer. And this was a business, just building a giant machine. But then, you know, a lot of these smart people like Google, Facebook, Netflix, all these guys realized that, hey, SQL is kind of terrible, you know, for large, big data problems. And though it's tried and true, it really doesn't handle, you know, petabytes of data. It just doesn't work at all. It struggles with gigabytes of data, to be honest, or really terabytes of data is where it really struggles. So kind of the biggest problem with the SQL database is they do not do full table scans well at all. And a lot of the technologies we'll talk about today are designed for full table scan data processing. So in the early 2000s, we had Bigtable, DynamoDB, and Cassandra. Cassandra was made by Facebook, and it was used by many different technologies. So Cassandra's birth was basically, you know, came out in 2005 for a NoSQL solution. So what is NoSQL? Well, you can pick your meaning. I think of it as a non-relational database. That's how I define it. So basically, it's an umbrella term for a lot of database technologies, and these databases were designed to solve specific problems. So if you look at a lot of code that you're probably working on at your current job, you're supporting some legacy monster that's been around for 10 years, you hate coding on it, and you need to migrate. Well, the reason why you can't migrate is people like Oracle made it so you could do everything on their platform. And because you can do everything on their platform, you can't take anything out of the platform. So the reason that NoSQL was developed was to solve for various different niches, right? So Oracle is not a graph database. Oracle is not a key value store. It's not a data warehouse. So kind of the big benefit of NoSQL is you're dealing with technologies that solve specific problems, right? So if you need in-fast memory data store, use Redis, and we'll cover that later today. If you need to do graphing, like doing vector and vertices analysis, that's when you use Neo4j. If you're doing column-based data, that's Cassandra. And if you're doing, document storage, that's something like Elasticsearch and MongoDB. So different data systems solve different problems, basically. So we have one database which handles many, many different servers. So all nodes participate in a cluster. Everything will share it as nothing. And if you need more capacity, you just simply add clusters. And because everything's designed for multiple servers, it is built-in redundancy. So some benefits of Cassandra, well, it's a linear scalable solution. So as you add more nodes, then you can add more reads and writes per second with a replication factor of 3. So let's talk about high availability. So basically, the head of IT operations for Outbrain, basically they lost an entire data center and their application was able to fail over, resulting in them losing just a few moments of serving requests for a particular region of the country. But their data in Cassandra never went offline. So their applications were able to fail over automatically and they're able to serve the data completely. So let's talk about the benefits to this approach. Well, basically, it's designed for writing. So Cassandra is a write-optimized database. So it really is like a perfect data warehouse for reliability. And you would generally query Cassandra as something like Spark or a programming language. What are the benefits to this approach that it's a distributed system? Well, you can make what's called a Raspberry Pi Beowulf cluster. So you could just stack a bunch of Raspberry Pis and run Cassandra on each of them. You can run it on a bunch of cheap old laptops or a very old server farm. So unlike something like Oracle, which used to use, proprietary Sun Solaris Spark processors, like no one wants to deal with that. No one wants to run Solaris anymore. So it's like, it's a very simple, horizontally scalable platform. What really is Cassandra? So Cassandra is a distributed hash table. That's what it really is. So basically you write your data to one node and then it replicates to 2 other nodes when you're looking at a replication factor of 3. What are the pros and cons of Cassandra? Well, basically, it's very fast. Your data is guaranteed to be always there. It's low latency, it's masterless, it's highly available, and as you add more nodes, it scales properly. The only downsides to it is it's not optimized for querying. So you can't join different columns, you can't do filtering, you can't really do good secondary indexing. So what you should do to solve these issues is do something like OLTP and design your request first and your model second. So unlike when you create a third normal form database, you design your requests and then you build your model around that. Versus a database where you do the third normal form and that takes a long time, and then you do everything after that. So what are the key differences between relational databases? Well, essentially, you have a data model design approach. So if a relational database, you build a model that reflects real-world entities, and then you build queries to join the data as you need it, and then you add more indexes. And with Cassandra, your design is based on the principle that the write and data storage are cheap, and you optimize the model based on how you want to retrieve the data. Let's look at query capability. So there are no joins. Aggregation is only with user-defined functions. And the restricted where clause is based on the table structure, and you can't do any stored procedures or views. So Cassandra is not designed like, MySQL or Oracle to have stored procedures, views. You're not going to create a bunch of crazy temp tables. You're not going to create functions. You don't do your code in Cassandra. You do your code in code. And that's kind of like when I go back to a few slides before, if you know SQL, stick to it, because there are a lot of, unfortunately, very antiquated engineering skills out there, which is just using SQL. If I was I would advocate using a programming language to solve your data issues. I wouldn't directly run stored procedures or any of that. It just gets out of hand. especially if you want to do distributed stuff. It just doesn't let you do that. Also, the big difference is there are no relational integrity functions like denormalized tables. There are transactions, but you can't, roll back a complete end-to-end operation. Like I said, Cassandra is not a programming language like SQL. SQL is actually a programming language and a data store. So if you treat SQL as a data store, you'll do fine. If you start writing all your queries in SQL, you'll run into some issues. Like you should really use an ORM tool, some kind of object relational mapping so you can interface between different data stores. Let's talk about CAP theorem. So basically, CAP theorem considers three things: consistency, availability, and fault tolerance. So every client has the same view of data. Every read receives the most recent write. Availability means every read and write request receives a response in a reasonable amount of time. And partition tolerance basically means that the system will continue to operate despite a number of messages being dropped by the network. So CAP theorem does not mean it's ACID compliant. ACID consistency means that data written to the DB are valid according to defined rules, constraints, and triggers. So in a distributed system, network failures always occur. You need to be partition tolerant. CAP theorem, you need to choose between consistency and availability. You can't always have both. And with Cassandra, you can have a balance with the level of consistency and availability that you want to choose. And Cassandra always favors availability. So if you have a data center go down, Cassandra is the most likely solution to survive a disaster. Use cases. So basically, I would treat Cassandra as a worldwide database. That's probably the best use case of them all. It automatically replicates the data, and it's designed for that kind of situation. It's also designed for people who are used to, using table-based data stores. So if you're coming from a SQL world, Cassandra makes some sense. Just make sure you also have some programming language. So takeaways. Databases used to be limited to a single server or mainframe. That's Oracle, MySQL. NoSQL is an alternative to data storage when it comes to databases. However, it does not do things like stored procedures, although it's kind of programming in SQL that you would do on SQL. But to be honest, you shouldn't really do that kind of stuff. You should use a programming language and then use a NoSQL to do your data parsing. And Cassandra is a no-value key store. Well, I'll take questions at the end. We have limited time. Okay. So now we're getting into Elasticsearch. So what is Elasticsearch? Well, remember how I said Cassandra is a perfect data store? Elasticsearch is the perfect search engine. What does that mean? Well, basically it's a open source distributed search and analytics engine built on Apache Lucene. So you basically put a bunch of data into Elasticsearch that you can query and visualize on something like Cassandra. So you could take some log files, some metrics, some documents, put them into Elasticsearch, which creates a RESTful API for you. And then you can get all sorts of output like application monitoring, security triggers, search engines, and infrastructure. But what is what is Apache Lucene? So Apache Lucene is a search engine written in Java, and it uses full text search. So it does like nearest neighbor algorithms, and it was designed to be run on a single node. And Elasticsearch basically takes Apache Lucene and makes it very scalable. Let's talk about the use cases of Elasticsearch. So if your boss comes in and he says, hey, I need you to find out why this application crashed, you'll start logging into all 30 of your machines and you're not going to gain any insights at all. And if you don't gain any insights at all, you're going to run into some issues. So you need something like Elasticsearch to query all of your logs simultaneously. Let's talk about the use cases of Elasticsearch. So basically, you can use Elasticsearch for logging, network monitoring, metrics, business analytics, security analytics, full text search, enterprise search, and autocomplete search. It's used by many enterprises such as, LinkedIn and Netflix, Slack, USAA, Facebook. Most of the use cases, though, are really around logging and log analysis, network and security monitoring, enterprise search. We also have security analytics and database monitoring. So who uses Elasticsearch? Well, it's growing. We have about 2,800 companies now worldwide that are using Elasticsearch. The benefits of it are it's scalable. It allows you to fully text search, so you can search a paragraph if you want. It's a completely RESTful interface, so you interact with it using, a website. And then you have RESTful APIs. You have a distributed approach, autocomplete search, fuzzy searching. It's document-oriented, it's schema-free, and it supports multiple languages, which is extremely important. What are the benefits of Elasticsearch? Well, it's scalable. It can scale horizontally. It's the same as Cassandra. You can have a 5-node cluster of Elasticsearch with primary and secondary nodes. It's a RESTful API, and it's distributed. Further benefits: full text search, fuzzy searching, autocomplete, instant search. Elasticsearch is a high-level search engine. Think of it as open source Google on your own private data center. That's really what it is, first and foremost. Multilingual support. It's fast because it's optimized for JSON, and you can use JSON, which is quite a good standard. Different Elasticsearch use cases? Well, IT operations, marketing insights, business developments, customer sentiment analysis, website search and internet search, and then you have internal systems and applications and external applications. Sorry, we have a question. Let's just quickly take a look. Yeah, we have used Elasticsearch to go through K8 logs. That is another webinar that we've given on AI Camp. I think you can find it on our website, or you can find out. We've definitely done it like a month ago. So that's a good question. In fact, I will send you a link because I am in a good mood, okay? Just Googling it. All right, for some reason I can't find it, but it's clearly in AI Camp slides. We can find out later after the fact. Let's move on.
Yeah, let me find it. I will post in the chat window.
Thank you. All right. So Elasticsearch is a NoSQL document store. It has no relations, no constraints, no joins, and no transactional behavior whatsoever, and it's easier to scale compared to a relational database. So Elasticsearch does indexing, it does types, it does documents, and it does fields. Relational databases are databases, stored procedures, SQL programming, all that horrible antiquated stuff no one likes to deal with anymore. So let's talk about cases where relational databases are not suitable, whereas Elasticsearch is a better candidate. You have relevance-based searching. You are searching when you've entered the spelling search term is wrong, so Elasticsearch does nearest neighbor kind of searching. Full text search, so if you want to search a paragraph of data, be my guest. Synonym search, so you can't run a SQL query looking for words like happy or words like sad. Elasticsearch can do that. It can do that. It can also do phonetic speech and logging analysis. So Elasticsearch is a very, very powerful analytics engine. It can basically take any JSON data and derive incredible value from it, just incredible value. So let's talk about Kafka, Kafka's my baby. I love Kafka. But before we talk about Kafka, let's talk about the importance of microservices and what they are. So a microservice is basically when you take a big monolithic web application that does everything, and you split it up into a handful of other processes. So you can pick up discrete business logic functions, say maybe authentication, logging, or user management, to do a specific thing, and you put this into its own application, and those different microservices can communicate since they are going to need to do that, and it's all done via HTTP. So what about microservices versus a monolithic architecture? Well, if you remember the giant Oracle server from a few screens ago, basically you'd have one database and that's it. You'd have a programming language that every single engineer does, and you have a QA team that would basically test it, find a bug, send it to engineering, then engineering would have to reproduce the bug on a staging environment, which is fun, and then roll out a new release. So the release management process was extremely slow. Thank you. Thank you. So basically in the microservices architecture, you still have one user that interacts with the UI, but these usually trigger independent microservices, which could have a shared database, or maybe each of them have their own database and they all do a very specific function. So let's discuss more about the advantages of microservices, right? So microservices provide fast value delivery. What that means is that we can fix, So because microservices are independent of everything else, you can quickly address that specific application. So what this means is that you can fix a component of the microservices much easier if we know that we can release and run it independently. We can implement new features faster because, we can put in just one component and it doesn't affect the rest of the whole topology. We can run experiments like all of a sudden we have new features and we can validate assumptions much faster. And this is super valuable because it allows the business to grow from like a cost center to a value producer, because in the old model, maintaining a monolith, you would need like 5 times the number of engineers. But on microservices, it's pretty nice. We can run experiments like we want to introduce new features and validate assumptions much faster. That's super valuable, but allows businesses to grow. We can increase the confidence in the development process, knowing that we can fix things easier and add new features easier. Microservices are language independent, so not everybody in your company needs to be doing Java or .NET. You could do whatever language you like to solve that particular business function. It really doesn't matter. The other advantages of microservices is you can split up each microservice into its own cross-functional team. In a monolithic architecture, you would have like, let's say 30 people. Yeah, so basically you would design redundant Srikanth, I'm just answering your question. All right, there you go. Your question's answered, sir. So a microservice can isolate faults and exceptions inside your program. So if one microservice fails, it doesn't necessarily mean that the entire application stack fails, especially if you're practicing a RESTful API and responding to the user through a user interface. So your backend and your front end are mutually exclusive. It's not like in a monolith where if there's an issue at the business logic, that may impact the front end. I don't know if any of you remember PHP programming, but if there's a syntax error, your whole website's down. Your database can't do anything. I mean, it was horrible. I'm so glad we're away from the LAMP stack. So microservices work well with containers. So you can containerize a single microservice, which makes it very scalable. And this is kind of the biggest advantages to microservices, that you can dynamically scale at any runtime. So again, this is why Google made a tremendously large investment in CoreOS, because microservices was the future. Unfortunately for CoreOS, every single distributor of Linux saw the same thing, and they built their own, and they open sourced it, and CoreOS was, boom, blown out of the water in 6 years. So what we're looking at here is, you can think of an event-driven microservice that is really self-contained, that can talk to each other over queues and topics. And the kind of thing you want to do here is to get all your microservices to talk together is through an event-driven platform. So you'd use some kind of message-oriented middleware or message bus, or what's called a distributed commit log, which is Kafka. So let's talk about Kafka. What was it? Well, basically, LinkedIn realized that they needed to basically fix a spaghetti code problem. Because before Kafka, any engineer can tell you there's spaghetti code. You'd be referencing one system, it would reference another. There'd be no like gatekeeper for everything. And that's why Kafka was invented as a unified distributed commit log. So LinkedIn has 1,400 brokers a day, billions of messages. Kafka usage is exploding. 1/3 of Fortune 500 companies use Kafka. A lot of them are used for complex event streaming systems, IoT platforms, in-memory microservices, streaming engines. Why would you consider Kafka? I apologize if I went too fast. So it's designed for stream processing. So it's a real-time streaming data processed for real-time analytics. So it's fast and scalable. It's like Cassandra. It's like Elasticsearch. It can handle 2 out of 3 of the machines in a cluster failing. So Kafka is a distributed system by default. And contrary to anyone who thinks so, you cannot run Kafka as a single node machine. That's just simply not possible. So Kafka is often used instead of RabbitMQ due to its higher throughput, reliability, and replication. Kafka is also used as a message-oriented middleware. Kafka has operational simplicity. It's set up and used, and it's easy to reason how Kafka works. However, the main reason Kafka is popular is because of its excellent performance. Basically, depending on the number of producers you assign to a Kafka topic, that means you can have more consumers working in parallel on those data streams, and you can have multiple data streams. So that's how Kafka is incredibly fast. You could have as many data streams as you want, and scalability is completely up to your imagination. You could have like one topic with 20,000 consumers for all I care. There's no limits to what you can do with Kafka. So let's talk about streaming. Kafka integrates very well with Flink, Spark, Storm, HBase, NiFi for real-time analytics and processing of data. And you can feed your data lakes with data streams. You can also look at KSQL. However, that's a Kafka-only solution. Kafka supports messaging streams that follow up for analytics, and Kafka can be used for all sorts of things. Also, the most important thing about Kafka is it doesn't care what kind of data you put in. Elasticsearch needs JSON, Cassandra needs a data structure, so you need to create a table. Kafka, you can just dump whatever you want. It's worse than Mongo. You could dump anything. As long as it's bits, it doesn't care. So how is Kafka so fast? Well, it uses the operating system kernel rather than a JVM to move data. So Cassandra is JVM based. You always have to deal with a lot of JVM tuning. Data is batched into chunks, and this could be end-to-end from the producer to the consumer. And you can also do data compression, which reduces I/O latency. Finally, you have sequential disk writes, and this avoids random disk access. What this basically means is an entry is always appended to the end of the log, so you're not inserting and incrementing the list. So anyone who studied computer science knows that if you insert an element into the list, you have to move the list forward. Kafka doesn't do that. It's an O of 1. That's right, O of 1 operation, both adding to it and reading from it. So that's how Kafka is very fast. It's O of 1 for reading, O of 1 for writing. I can't stress that enough. Like a SQL database has nothing on Kafka. It's like 1 billion times slower. Horizontal scale. So the more partitions you have, the more you can read that data in parallel. So that's how Kafka scales. And finally, it's low latency. It can respond in a matter of milliseconds. Let's talk about Kafka versus traditional message queues. So traditional queuing systems, well, they usually discard messages. So after a message is processed by most messaging systems, the message is gone. FIFO-based systems, basically the consumer is just FIFO-based, reading from the head. No, do not use Kafka as a permanent data store. I don't care what you've read on Confluent. I don't care what their marketing stuff says. Don't use it as your permanent data store. Use a database, use Cassandra. Things that are designed to store data should store data. Kafka is not a data store. Confluent will say otherwise. I'm telling you right here on this call, don't use Kafka as a permanent data store. All right. Or use like S3 in the cloud. So it does say in the screen, Kafka is a semi-persistent data store. By default, it stores data for 7 days. Technically, you could tell it to store data forever. The problem with storing data forever is, well, it's not optimized to index and search data. It's literally just a giant log file. So if you need to read from the beginning of the file to the end, if you're talking terabytes of data, that could take a long time. There's no indexing whatsoever in Kafka. It's a real-time data engine, that's it. So Kafka will replicate messages and it can handle failure. And probably the most important thing is Kafka is horizontally scalable. You can have as many brokers as you want in a cluster. RabbitMQ is literally limited to 3 to 5. I think IBMQ is like just one machine or something, one supercomputer. Anyway, so what are the use cases of Kafka? Messaging, metrics, website activity tracking, log aggregation, stream processing, event sourcing, and probably the most important thing is a distributed commit log. And it's used by a lot of companies and it has a massive adaptation. Use it to do activity data, operational metrics. Twitter uses it for stream processing. Square uses it as a central event system hub. All right, that's it for Kafka. Let's get into the next step. Redis. Oh, I love Redis. So Redis was created by Salvatore Sanfilippo, and he started the company Redis Labs in 2011. What does it feature? Well, basically, it's a key value store. It has sets, strings, and dictionaries. It does a time to live and LRU. You can have as many nodes as you want of Redis. It's all just memory. So as many machines have memory available, you could have thousands of nodes. It's elegant and simple. It's usually used for just like a really fast, like caching, user profiling. I've used it before for like a publish and subscribe system for a website. Technically, you could stream on it too, like Kafka. So then you have to decide, where's your streaming going to go, Redis or Kafka? I'll actually tell you at the end of this, you shouldn't use either for streaming. Disks persistent. So you have the ability to basically write your data in Redis to a more permanent data store. Use cases, caching, real-time API traffic. Gaming is a massive use of Redis. Like gaming, everything's all about speed. Websites, UI, UX, increasing your time budget. Maybe you just need to do things faster and stream processing. So let's talk about the market share of all these systems. So as you can see, Cassandra is like 3.9%. MySQL, Postgres, SQL Server, that's pretty much a majority of the entire market. And then Mongo is like 20%. Redis is 20%, heavy usage. What is the most loved, dreaded, and wanted database? Well, it's Redis. Why is it the most loved and hated and wanted at the same time? Well, it's all in memory. So imagine pulling the plug on your computer and you lose everything. That's kind of what Redis is. It's all in memory. It's really fast and it has some caveats. So that's kind of what it is. Caching example. So basically, whenever you're like going to a website and you see some music that would normally be stored in Redis, so the user can quickly read up for it. So think of it as a good a lookup table, like a very fast lookup table or a variable in your code. Let's talk about Twitter. Well, they have 3,000 Redis instances. They do 10 million queries a second and 10 terabytes of data in memory. That's right, 10 terabytes of data in memory. Let's talk about disk performance. Well, speed matters. Performance plays a major role in the success of any online venture, and there are some case studies below to talk about it. So Pinterest increased search engine traffic and signups by 15% when they reduced perceived wait times by 40%. So they increased the direct number of signups by 40% when they reduced speed times. There's a risk matrix, so the risk severity. Yeah. So I like Redis. It's all these technologies are hyper cool, according to this graphic. So let's talk about how do you link everything together. This kind of sounds overwhelming, right? Like we talked about old school databases, Cassandra, Kafka, Elasticsearch. I don't know. It's out of hand. I'll tell you. So think of it this way. Cassandra is your long-term data storage, right? It's your data storage engine. Think of it as your data warehouse. And Hadoop. Like Cassandra and Hadoop are permanent data stores. And Hadoop is your distributed database. Then your processing engine is up to you as an engineer. You know, I like Python. Other people like Flink. Some like Spark. Some like NiFi. Then there's also some very new technologies that are exciting, like Apache Camel. That came out. That's at ApacheCon this year. Apache Calcite is something I'm feverishly interested in seeing more about. Apache Calcite takes us back to the beginning. It's a SQL engine for any technology in the world. Also, there's things like PrestoDB, but Calcite is very promising based on the quality of the contributors to it. So how do we link everything together? Well, we use Kafka as our bread and butter, as our highway, as our data pipeline. So Kafka is a really good, platform for integrating different things. So when you want to pull in a bunch of other systems, like on the left-hand side and on the right-hand side, you would use Kafka, and then you would process that data using your engine of the choice, which could be, in this example, would be Python. But if you need to do Spark and Flink and NiFi, all of these, then you can run it in your data processing engine. So let's quickly cover event-based data flow workflow modeling. So generally speaking, you want to think of the problem you're trying to solve. You want to think of the input. If I wanted to determine Trump's travels and mood, we have to think of the input. Where can we get this information? Well, we can get it from Twitter. How do we get his Twitter data? Well, we would pull it somehow using a Kafka producer, which would write to a topic, and then we would build a machine learning model. So we would pull in the tweets, we would partition it into a Twitter topic, and then we would perform sentiment analysis on those tweets. And believe me, there's plenty of Python libraries that do this in APIs. It's actually pretty straightforward. Once we have the results we want, we write that to a moods topic, and then we write a consumer to average it, and we publish our results to Elasticsearch. Now, why would I use Elasticsearch? Well, it's fairly straightforward. What we would do is we'd use Elasticsearch to build powerful user interfaces and data-driven dashboards. So Elasticsearch is a completely open source data front end. That's what it is. It allows you to build these amazing charts with very little effort. So you don't have to spend, months of time learning D3 or other, complicated front-end engineering skills. Just use Kibana. It'll just work. You just got to model your data accordingly. So Elasticsearch is fantastic for building rich user interfaces. So how do we build a proper open source solution and picking the right tool for the right job? Well, this is how we combine all the technologies, right? You use a Kafka connector to pull the data. That's like the easiest way to write it. And then you write something through Kafka called a Kafka connector that will let you sync the data into Cassandra and then sync it also into Elasticsearch. You'll also write your data processing engine in your tool of choice. So that could be Spark, I personally use Python because Python's easy. If you want to do AI, you could do TensorFlow on your Kafka queues. That's completely fine. Maybe we'll do that in the future. But if you're interested, the code base is right here. Maybe I can. All right. So here's the code base if you guys want to check it out. Figure out how this Kafka, Elasticsearch, Cassandra magic all works. Be my guest. So I guess we have 3 minutes left. What kind of questions do you have for me? You can unmute your microphone, ask some questions, or you can type it in the chat. Up to you.
Yeah, great. If you have questions, you can type in the Q&A, or if you want to prefer to speak, you can raise your hand. We will unmute you to speak.
Yes, Srikant, that's a good question. So if I go back to the beginning, so Elasticsearch has what are called primary nodes and secondary nodes. Some are what are called the search nodes. Others are called the indexing nodes. So the search nodes are like the front end of Elasticsearch, and the indexing nodes are the back end, and they build the indexes for searching. So you can add more nodes, and you would do it on each index itself. So each index would be stored on either one or more machines, and you can define that yourself. And Elasticsearch is a clustering technology. So just like Kafka, it can scale to basically a large number of machines, and you can run some queries on it. I hope I answered your question.
There's a question in the chat.
I see that. You should ask it. Is there a good way to practice this? Yeah, I mean, that's a good question, Tiffany. And I know it's a tough job market out there. So like I said, it's in the chat window. I gave the code base. That's a pretty good starting place. If I was fresh out of college, yeah, I think the code base I have is a good starting point, because basically you have all the data ingesters written. It has all the technology. It's all in Docker, so you don't have to figure anything else out. But if you're trying to learn like Cassandra, do a Cassandra tutorial. If you want to learn Kafka, do a Kafka tutorial. If you want to do Elasticsearch, do an Elasticsearch tutorial. And then after you do all that, then check out my open source GitHub. That should get you much further along. I hope I answered your question. There you go, Tiffany. Thank you, Chris. Guys, you can ask me any question in the world. I'm here 24/7, just like Instaclustr. Yeah, so Apache Druid is an interesting platform. It's basically like Elasticsearch. It is a processing platform, and it should theoretically integrate with Kafka. That's all I know right now. I don't have any serious experience. Yeah, so Flink, if you see in my diagram over, hold on. This is why we have these sessions, right? Just trying to find it. So Flink is a processing engine, basically. That's kind of what it is. So Flink is like Spark. It's also like Beam. Basically what you would use is you'd put Spark in the middle of this diagram here. So you'd process your real-time data with Beam, Flink, or Spark, NiFi. All of that would go into Kafka, where you would basically read the data from the Kafka stack, process it in some way, and then send it to another Kafka topic, and then let the rest of your pipeline handle it. So you basically design everything with like an if this, then that pattern. Like if this, then do that, if this, then do that. That's kind of the way to think about it. I hope I answered your questions. Edge computing. Unfortunately, I've heard of that term before, but it's kind of leaving my brain. Please send me an email. What is edge computing? I'll look that up later. All right. Yeah, Ruth, and basically it's a different kind of philosophy. So with something like NoSQL, you use specific technologies to solve a specific problem. And if you decide to go with a SQL stack, like the Oracle stack, you're pretty much locked into that ecosystem. So what that means is you have things like stored procedures in SQL. You have things like views, all these things that are in the SQL engine. And the risk with this is that you can't put your database into version control. So, it's much harder to do that with SQL. And the benefit of Elasticsearch is the querying is just much more high level. You're asking, natural language processing questions to a data store. You just can't possibly do that with SQL. So those are the two issues with SQL. You're completely invested in it. It's very hard to turn into a microservice. Believe me, I know. I spent a year trying to take a MySQL database into a Docker. And you can't really run things that are like full text search. I mean, maybe you can, but it's not a data set designed for, the next level of computer science, which is machine learning, fuzzy logic, natural language processing. It's usually a single-threaded solution too. I mean, I know there are solutions out there like Vitesse, but they're not designed for it. Oh yeah, let me put my email here. Just send me an email. I feel so bad. This should have definitely been like 2 hours, not an hour, but that's okay. Send me an email. I'll be happy to answer it. Sharing a database to store data. Yeah, you don't want to share a database because what's going to happen is there's a risk of deadlocks. So that's kind of why I don't like SQL databases. Whenever you're reading and whenever you're updating a row, you're basically locking it. And when you lock a row, that could cause a deadlock. When you use a NoSQL solution, they're designed to scale against this issue. I think that concludes our workshop. Any questions? Well, I mean, there's a lot of questions. Please send me an email.
All right. Okay, great. Thanks a lot, Zach, for the presentation and talk. And thank you, everyone, for all of the questions. I know you probably have more questions. And we actually have another sessions on Kafka workshop on August 18. That is about 2 weeks from today. That is actually the workshop for 3 hours. So we're going to have more content, more hands-on, and more times to talk about the Kafka and its related technologies. You also can post the questions in the Slack. I think we are on the Slack, the channel. So you can post questions over there if you cannot wait until August 18.
Thank
So
you, Jens,
that's
for your comment. My no